Good evening, all. Welcome to discussion session for the NPTEL course Soil Mechanics Geotechnical Engineering 1. I shall share my screen now. This is a recorded session for the live discussion session 6, which was cancelled due to some unavoidable circumstances earlier. So let's begin this discussion session. First question is, in the Morse diagram, a point above the Morse envelope indicates. So, if we have a Morse stress diagram or the Morse circle, if we consider the Morse failure envelope, the point above the Morse envelope indicates option A, imaginary condition, option B, safe condition, option C, imminent failure condition, option D, condition of maximum obliquity. So, what does a point above the Morse envelope indicate? So, point above the Morse envelope indicates imaginary condition. That is, a stress point above the failure envelope does not show any stress condition as shown in the figure. So, a Morse circle or Morse diagram is plotted with direct stress or normal stress on the x axis and shear stress on the y axis. C represents the cohesion and phi the angle of shearing resistance. And the failure envelope is drawn tangential to the Morse circles. So, as we can see, the point A, which lies above the failure envelope, does not show any stress condition for the considered criteria or the material. So, the condition of a stress point above the failure plane always indicates an imaginary condition as it does not show any stress condition. All right. So, coming to the second question, for pure clay, the shear strength parameters will be statement 1, cohesion C is 0 and angle of shearing resistance phi will be maximum. Statement 2, cohesion C is maximum and angle of shearing resistance phi is also maximum. Statement 3, angle of shearing resistance phi is 0 with some value of cohesion C. So, for pure clay, the shear strength parameters will be which of these statements? Option A 1, 2, and 3. Option B 1 only. Option C 3 only. Option D 1 only. Which will be the correct option? Yes, the correct option is option C, that is 3 only. So, if we check each one of the statement, first statement says that cohesion C is 0, but the soil sample given is pure clay. We know that clay is a cohesive soil and so it will have some value of cohesion. So, cohesion C cannot be 0. So, first statement can be ruled out. Then second statement is cohesion C is maximum. We cannot say that cohesion C is maximum, but it does have some value of cohesion. So, coming to third statement, and also the second statement says that angle of shearing resistance phi is maximum. But for pure clay, angle of shearing resistance phi is 0. So, we can rule out second statement as well. So, the only correct statement or the only possible shear strength parameter for a pure clay is that there will be some value for cohesion C and the angle of shearing resistance phi will be 0. So if we see the Morse diagram and the failure envelope for pure clay, we can see that the failure envelope is a straight line parallel to x-axis with angle of shearing resistance phi 0 and some value of cohesion C. Moving on to the third question, we have the plane on which shear stress is the maximum, the normal stress on that plane is. So we have a plane where the shear stress is maximum. Then what will be the value of normal stress? Option A 0. Option B less than minor principal stress. Option C greater than major principal stress. Option D half the summation of major and minor principal stress. So what will be the normal stress on a plane with maximum shear stress? So correct option is option B, that is the normal stress on the plane of maximum shear stress is half the summation of major and minor principal stress. So if we see in this figure of Morse diagram, we can see that point A represents the maximum direct stress and point B represents the minimum direct stress with zero shear stress. So that is a principal plane with zero shear stress and maximum and minimum normal stress at points A and B respectively. The maximum shear stress plane is represented by C. That is in the positive y direction towards the point C is the maximum shear stress, and the maximum shear stress plane is this particular plane. So the value of normal stress in that plane will be this distance, that is sigma 1 plus sigma 2 by 2, because from here to A we have sigma 1 and from origin to B we have sigma 2. So we need the distance or the radius of this particular circle plus this distance. So from origin to this particular center of the circle is the required normal stress. So that value will be equal to sigma 1 plus sigma 2 by 2. That is the sigma 2 plus radius of this. That is sigma 1 minus this value, and sigma 1 minus this will give the total diameter. Half of that plus sigma 2 will give the required normal stress. That is sigma 1 plus sigma 2 by 2. Is that clear? I'll explain once again. So actual value that we need is the normal stress in this particular plane. That means the distance from origin to the center of the circle. Distance from origin to point A is the maximum normal stress, and origin to B is minimum normal stress. So the diameter is actually sigma max minus sigma min, or sigma 1 minus sigma 2, as in this case we have represented sigma max by sigma 1 and sigma min by sigma 2. So the diameter is sigma max by sigma min, or sigma 1 by sigma 1 minus sigma 2. So we need the radius plus sigma 2, that is sigma 1 minus sigma 2 the whole by 2 plus sigma 2, which will give you sigma 1 plus sigma 2 by 2. Alright. So moving on to our fourth question. If the Mohr circle for a given state of stress lies entirely below the Mohr envelope for a soil, then state of the soil for that state of stress is. So we have a Mohr circle for a particular state of stress, and we have a Mohr envelope for that particular soil. If our Mohr circle is falling entirely below the Mohr envelope, what will be the state of stress What will be the state of the soil for that particular state of stress? Option A, unstable. Option B, stable. Option C, failure state. Option D, can't say anything. So we have a failure plane or failure envelope, and our Mohr circle for this particular soil lies entirely below the Mohr envelope. Then, state of the soil for that state of stress is, correct answer is option B, that is, it will be stable because, because our Mohr circle for the given state of stress is below the Mohr envelope, that is, it is in the safer zone. It is not touching the failure envelope. So it is completely stable. Okay, so moving on to the fifth question. The plane of maximum shear stress makes an angle of dashed with the principal plane. So what is the angle between plane of maximum shear stress and the principal plane? What is the angle between plane of maximum shear stress and principal plane? Yes, the angle will be 45 degrees. The plane of maximum shear stress and the principal plane is at an angle 45 degrees. So moving on to our next question. If a soil has a cohesion of 10 kilonewton per meter square and an angle of internal friction of 25 degrees, the normal stress acting on any plane within the soil is 34 kilonewton per meter square. The shear strength of the soil is, so we are given cohesion, angle of internal friction, and the normal stress acting on any plane. We are asked to determine shear strength of the soil. Option A 41.2, option B 32.4, option C 21.7, option D 25.8. So the correct option is option D. Here we are given cohesion C as 10 kilonewton per meter square, angle of internal friction or shearing resistance as 25 degrees, normal stress acting on any plane within the soil as 34 kilonewton per meter square. So, shear strength of the soil is given by the equation S is equal to C plus sigma tan phi. All the values are provided in the question. By substituting, we have S is equal to 10 plus 34 tan 25, which will give you 25.85 kilonewton per meter square. Hope it's clear. Moving on to the next question. The effective stress friction angle of a saturated cohesionless soil is 45 degrees. The ratio of normal effective stress to shear stress on the failure plane is, so we are given a saturated cohesionless soil and the effective stress friction angle of the particular soil is 45 degrees. We are asked to determine the ratio of normal effective stress to shear stress on the failure plane. Option A zero point 0.7, option B 1, option C 2, option D zero point 0.5. So the correct option is option B 1. Here we are given that the cohesion C For given cohesionless soil will be 0 because it is a cohesionless soil. So the value of cohesion will be 0. It's given that the angle of internal friction of this particular soil is 45 degrees. Therefore, considering the equation for the shear strength, we have S is equal to C plus sigma tan phi. Here, C is 0 and phi is given as 45 degrees. We are asked to determine the ratio of shear strength and effective stress or normal stress, which we have S by sigma is equal to 1. That is option B. Moving on to the next question. The subsoil at a site consists of 10-meter thick homogeneous layer of dense sand having dry unit weight 17.2 kilonewton per meter cube. Specific gravity of the soil is equal to 2.68 and angle of internal friction phi is equal to 30 degrees. The natural groundwater table lies at 2.5 meter below the ground surface. Assume that the soil is dry above the water table and unit weight of water is 10 kilonewton per meter square. The shear strength of the soil along a horizontal plane through the middle of the sand layer will be. So we are given a subsoil with 10-meter thick homogeneous layer of dense sand. Dry unit weight of the sand sample given is 17.2 kilonewton per meter cube. Specific gravity of the soil sample is 2.68 and angle of internal friction is given as 30 degrees. It is also mentioned that the natural groundwater table is at 2.5 meter below the ground surface. Above the water table, the soil is mentioned as dry, and we are asked to determine shear strength of the soil at a horizontal plane through the middle of the sand layer, that is at 5-meter thickness. Option A 54.82, option B 71.47, option C 44.77, option D 61.57. So the correct option is option A, that is 54.82. So let's see how to solve this. We are given that the thickness of the sand layer is 10 meter. Dry unit weight of sand is 17.2 kilonewton per meter cube. Specific gravity of sand is 2.68. Angle of internal friction phi is 30 degrees. Depth of natural groundwater table is 2.5 meter below the ground surface, that is within our sand layer. And unit weight of water is given as 10 kilonewton per meter square. So, considering the equation for shear strength as in the previous problems, we have S is equal to C plus sigma tan phi. So, since this is sandy soil, cohesion C will be 0. We need to determine sigma. Phi is given as 30 degrees. So, for sandy soil, cohesion C is 0. So, we have S is equal to sigma tan phi. Now, overburden stress, that is sigma at the middle layer, is equal to 2.5 times dry unit weight of the soil, that is the soil above the water table, because our water table is at a depth of 2.5 meter from the ground surface. Above that water table, we are asked to consider the soil as dry. So, the stress induced by that dry soil is 2.5 times gamma d, depth into gamma d, plus the remaining soil up to the middle layer, up to the middle of the sand layer. That is, we are calculating the shear strength at the middle of the sand layer or 5 meter from the ground surface. So, deducting the first 2.5 meter dry soil, we have the remaining 2.5 meter saturated soil. So, the overburden stress induced by that saturated soil layer will be 10 by 2, that is 5 minus 2.5 into gamma saturated. Now we know that dry unit weight is equal to G gamma W by 1 plus E, which is given as 17.2 in the question. Dry unit weight of the soil is given as 17.2 in the question. So E is equal to, from the equation rearranging, we have E is equal to G gamma W by gamma D minus 1. That is 2.68 into 10 by 17.2 minus 1, which is equal to 0.558. Now we can calculate gamma saturated, because for calculating overburden stress, we need both dry unit weight as well as the saturated unit weight of the sandy soil. Dry unit weight of the sandy soil is already given in the question as 17.2. Now, for the saturated unit weight, the equation we have is G plus E into gamma W by 1 plus E. But E value was unknown, and so we used the equation for dry unit weight to determine the value of void ratio E. Now, back substituting in the equation for saturated unit weight, we have gamma saturated is equal to 2.68 plus 0.558 whole into 10, the whole divided by 1 plus 0.558, which will give you 20.783 kilonewton per meter cube as the gamma saturated value. Now, we have shear strength S is equal to sigma tan phi. So, sigma is equal to 2.5 into 17.2, that is 2.5 gamma d, plus 5 minus 2.5, that is the remaining 2.5 depth of saturated soil, into gamma saturated, that is 20.783. Substituting in the shear strength equation, we have S is equal to 94.957 tan 30, which is equal to 54.82 kilonewton per meter square, is the required shear strength of the soil along a horizontal plane through the middle layer of the given sand layer. Moving on to the next question. For the given state of stress shown in figure, find out the principal stresses. Also, determine the orientation of the planes of these principal stresses with x-axis. So we have option A, maximum principal stress is equal to minus 25.51 megapascal. Minimum principal stress is equal to minus 130.51 megapascal. Theta P is equal to minus 44.54 degrees, and 49.61 degrees. Option B, sigma max is equal to minus 25.51 megapascal. Sigma min is equal to 130.51 megapascal. Theta p is equal to 40.39 degrees and 49.61 degrees. Option C, sigma max is equal to 25.51 megapascal. Sigma min is equal to minus 130.51 megapascal. Theta p is equal to minus 40.39 degrees and 49.61 degrees. Option D, sigma max is equal to 25.51 megapascal. Sigma minimum is equal to 130.51 megapascal. Theta p is equal to 44.54 degrees and 55.61 degrees. So, the given state of stress is shown in the figure, that is both element state of stress as well as sign convention is shown. So, the stresses are given as 40, 65 and 77. That is sigma 1, sigma 2 and shear stress respectively. So, we'll see what is the correct option. Correct option is option C, that is sigma max is equal to 25.51 megapascal, sigma minimum is equal to minus 130.51 megapascal, theta p is equal to minus 40.39 degrees and 49.61 degrees. Okay, so we'll see how to solve this. We are given that sigma x is equal to minus 40 megapascal, sigma y is equal to minus 65 megapascal, and tau xy is equal to 77 megapascal. Now, why we have taken this negative and positive is because of the given sign convention. When we see the given sign convention, that is the positive sign convention, only shear stress is in the positive direction in the given question, that is 77. Both the other values, sigma x and sigma y, is in the opposite direction or the negative. So we have sigma x as minus 40 megapascal, sigma y as minus 65 megapascal, and tau xy as 77 megapascal. Okay, now sigma max is given by the equation sigma x plus sigma y by 2 plus square root of sigma x minus sigma y by 2 the whole square plus tau square xy. Sigma minimum is equal to sigma x plus sigma y by 2 minus square root of sigma x minus sigma y by 2 the whole square plus tau xy square. And tan 2 theta p is equal to minus 2 tau xy by sigma x minus sigma y. So these are the three values that we need to determine: sigma max, sigma min, and theta p. Substituting the values, we have sigma max is equal to minus 40 minus 65 by 2, that is sigma x plus sigma y by 2, plus square root of minus 40 minus 65 by 2 the whole square plus 77 square, which will give us 25.51 megapascal. Now, minimum principal stress sigma minimum is equal to minus 40 minus 65 by 2 minus square root of minus 40 minus of minus 65 by 2 the whole square plus 77 square, which is equal to minus 130.51 megapascal. And tan 2 theta p is equal to minus 2 into 77 divided by minus 40 minus of minus 65, which is equal to minus 6.16. Taking the in tan inverse, we have 2 theta p is equal to minus 80.78 or 180 plus this value, and theta p is equal to half of this, which is minus 40.39 degrees or 49.61 degrees. So now here we have some practice problems. You may please note down. Question 1. The principal stresses at a point in a material are 80 kilonewton per meter square and 40 kilonewton per meter square. Determine the normal, shear, and resultant stress on a plane inclined at 30 degree to the major principal plane. So the principal stresses are given as 80 kilonewton per meter square and 40 kilonewton per meter square. We are asked to determine the normal stress, shear stress, and resultant stress on a plane that is inclined at 30 degree to the major principal plane. Question number 2. On a failure plane in a cohesionless soil sample, the normal and shear stresses are found as 10 kilonewton per meter square and 4 kilonewton per meter square. Determine the resultant stress on the plane of failure, the angle of shearing resistance, and inclination of failure plane to the major principal plane. Okay, with this, we come to an end to the discussion, uh, full substitution of the live discussion session 6. Thank you all.